Alright, let's get started. Today we're going to talk about types of chemical reactions and aqueous solutions. So, we're going to talk about some general properties of aqueous solutions, and when we're talking about aqueous solutions, we're talking about materials that are basically dissolved in water-based media. Now, a solution is a homogeneous mixture that comprises basically your solute and your solvent. Now, a solute is a component that is dissolved, and your solvent is a component that does the dissolving. Generally, the component present in the greatest quantity is considered to be the solvent. Aqueous solutions are those in which water acts as the solvent. Electrolytes and non-electrolytes. Well, electrolytes are the substances that are dissolved in water and it produces electricity. Many times there are solutions that you consume that feature electrolytes. For instance, one such example lies in that I think the trademark Gatorade, and it is packed with many materials that are dissolved in water that are capable of conducting electricity. Now, these things actually contain ions. One popular such example is that of NaCl, affectionately table salt. This dissolves into the ions sodium and chloride. Now, a non-electrolyte is a substance that dissolves in water and it produces a solution that does not conduct electricity. A notable example can be seen when you put sugar in water, and that's because these do not contain any ions whatsoever. So now you have a distinction of understanding the difference between electrolytes and non-electrolytes. Now, along the concept of electrolytes, they undergo dissociation. Now, this process is when ionic compounds separate into constituent ions and are dissolved into the solution medium. Now, during the process of ionization, you have formation of ions by molecular compounds when they're dissolved. An example is shown below. Strong and weak electrolytes. First of all, a strong electrolyte is capable of dissociating at 100%. That means they're capable of being broken down into their constituent ions. Now, all water-soluble ionic compounds are included, as well as strong acids and strong bases. Conversely, weak electrolytes do not dissociate completely. They undergo partial ionization or partial dissociation in solution. And they exist mostly as the molecular form in a solution. This will also include weak acids and weak bases. So the take home here is that strong acids, strong bases, and many soluble ionic compounds are capable of 100% dissociation in solution, whereas the weak electrolytes, which comprise the weak acids, weak bases, tend to partially ionize and exist mostly as their molecular form. So, looking at this chart, this is just a general list of strong acids, which include hydrochloric, hydrobromic, hydroiodic, nitric, chloric, perchloric, and sulfuric. And these are some notable examples that you would want to add to your repertoire of knowledge regarding strong acids. Now, to recap, there are examples of weak electrolytes, and again, restating, they have a tendency of partially ionizing, and therefore, that is generally represented using double arrows to represent that not only does the reaction go forward, but it has the capacity to lean towards going back, and it can be heavily influenced by the ability to dissociate by the weak acid or weak base in question. Once again, I took the time to highlight that with weak acids and weak bases, because they partially ionize, they have double arrows to indicate this. This means that not only does the reaction go forward, but it has the capacity to go backward as well. Now, method to distinguish types of electrolytes. Well, in a practical example, one could simply set up a light bulb experiment and As I stated before, strong electrolytes are capable of producing electric current. Non-electrolytes, like the sugar and water, would result or yield no current, or electrical current rather, and weak electrolytes would produce partial current. And so that's kind of evidenced by the lighting from the images provided. Now, precipitation reactions. Now, the word precipitation represents the formation of a solid from two aqueous solutions. This occurs when a product is insoluble. They generally produce insoluble ionic compounds. Now, solubility, as a definition, is the maximum amount of a solid that can dissolve in a given amount of a solvent at a specified temperature. So this means that solubility can be heavily influenced by the nature of the solid, as well as by the temperature and the solvent present. Now, most predictions of solubility are based on kind of a chart of rules, and you can diagnose the potential for solubility based on these rules of certain substances. Now, when it comes down to solubility, you will want to commit these rules to memory as best you can. Now, there's a league of compounds that are actually water-soluble compounds, and when paired with other compounds, they lean towards remaining soluble. However, there are some exceptions that will remain insoluble. You will want to be knowledgeable of both the included and the exceptions to the solubility rules. So just take a look at the list. If you don't already have your own list, you'll want to review these, as there will be questions that probably are asked regarding solubility and insolubility of compounds that are formed. Hydration. Now, this is an interesting process by which water molecules remove and surround individual ions from the solid. So it gets around the ions, surrounds them, and they're dispersed and allowed to kind of move around, or dissolved rather. Now, as I highlighted before, we were talking about the idea of insolubility. In a scenario where you mix lead nitrate with sodium chloride, it produces a precipitate, which is an insoluble material. Now, in the image, the yellow precipitate that's formed from the mixing of the two aqueous media is actually lead iodide. More specifically, however, lead 2 iodide. So, when you're looking at the product, you notice that there's this yellow formation of material that has settled to the bottom. This is precipitate, and it comes in a variety of colors. It can range from white or blue, depending on the nature of the materials that are mixed together as aqueous media. Knowing the rules about solubility can help predict whether a product formed will be perhaps soluble or insoluble in water. Now, molecular equation. This shows all compounds represented by their chemical formulas. The Ionic Equation shows all strong electrolytes as ions and all other substances. This includes non-electrolytes, weak electrolytes, gases by the chemical formulas. Now, as I stated, the molecular equation can be seen above. What makes it unique from the Ionic Equation is that the Ionic Equation looks at the ionic form of the equation, where the ions are broken down into their respective individual ions. Now, for the net ionic equation, we are only shown the reactant species in the chemical equation, which prompts you to remove something called a spectator ion. Now, the spectator ion is an ion that is not directly affiliated with a reaction, and a lot of times can be removed based on the fact that they are present. So, for example, here we have sodium, which is removed, as it is seen on both sides of the reaction. We also have hydroxide group that is found on both sides of the reaction. What is interesting to note is that when you're referring to your spectator ion, you're looking for the compound that is found on both the reactant and product side. And once eliminated, rewritten, the net ionic equation can be represented. In this case, it shows the barium ion plus the sulfate ion yielding barium sulfate. Now, there are some important steps in writing a net ionic equation. First, you want to write the balanced molecular equation. Then you want to predict the products by exchanging the cations and anions that are associated with the reactants. Then you want to separate strong electrolytes into their respective ions, recalling that strong electrolytes tend to dissociate at 100%, whereas the weaker ones do not. Then you want to go forward with canceling the spectator ions. You want to then use the remaining species to write the net ionic equation. This means that you eliminate the ions that are repeated on both the left and the right. Now, in such example, we have aqueous solutions of silver nitrate and sodium sulfate that are mixed. They will task us with writing the net ionic reaction for this. Step 1 means that we will write the balanced molecular equation. This means we understand that silver nitrate, written to be reacted with sodium sulfate, would produce sodium nitrate and silver sulfate as the products. In step 2, you want to use the solubility table, which predicts the ability to be soluble in solution. Now, all nitrates are soluble, but silver sulfate is insoluble. And so when you look at it and you rewrite the equation, you write that with the understanding that the silver sulfate is insoluble and therefore not broken down into its respective ions. In step 3, you next wish to cancel the spectator ions. Recall, these are the ions that are found both commonly on the left and the right hand side of an ionic equation. Finally, after removing these spectator ions, you next want to write down the net ionic reaction. When written, it would look like this. Now, switching gears here, we like to talk about acids and base reactions. Now, these are termed neutralization reactions, mostly because they act on opposing forces of pH and they tend to neutralize each other. They require an acid and a base to be called an acid-base reaction, and more common than ever, they form products that feature salt and water. Now, some notable examples of weak bases and weak acids include two of the following. One is ammonium with water, in which when you react ammonium with water, you have the double arrow, which denotes that the reaction does not go to complete ionization. And this means that you can reform the starting reagents. Another example is hydrofluoric acid and water, further evidenced by the double arrows. Now, continuing about acids and bases, let's go ahead and define these words for acid. There's arenous acid, which produces hydrogen ions in solution. There are arenous bases, which produce hydroxide ions in solution. Going forward, there are other inclusive definitions, one of which includes the Bronsted-Lowry acid, which is a proton donor, and the Bronsted-Lowry base, which is a proton acceptor. Now, for types of acids, there are protic acids. This means there's a certain number of protons. There's monoprotic, there's diprotic, triprotic, and polyprotic. Monoprotic means that there's one ionizable hydrogen. Diprotic means there are two ionizable hydrogens. Triprotic means there are three ionizable hydrogens. And polyprotic is a generic term meaning more than one ionizable hydrogen. Now, the ionizable hydrogen represented here goes to the root word of mono. In this case, we're talking about one proton, which in this case would be one hydrogen. Here for diproduct, we have two hydrogens that are ionizable. It gets ionized in this step and can be ionized in the second. Here we have our triprotic, where in the triprotic we have three ionizable hydrogens. It is important to understand that as you go up in the number of ionizable hydrogens, the ability to ionize the hydrogen becomes a little bit more difficult. Now, types of bases. There are monobasic, in which you have one hydroxide ion group, or there are examples where you might have dibasic, where there's two hydroxide ion groups. Now, continuous acid-base neutralization. Now, the neutralization is a reaction between an acid and a base. In this case, you react an acid with a base to yield a salt plus water. Now, for the molecular equation given, this represents a notable example of a strong acid paired with a strong base that then yields a salt plus a water. Rewritten, an ionic equation would be represented in the following way, in which you would have hydrogen ion broken up to form the chloride ion, and then you'd have a sodium ion and a hydroxide ion. And this would yield the sodium ion, the chloride ion, and water. Recalling the steps from before, when breaking down net ionic equations, you would remove the spectator ions, in which case would be the chloride and the sodium. This would yield the net ionic equation of the following. Oxidation reduction reactions. Now, these are affectionately called redox reactions for short. It's when you take the abbreviation of the re and you add the the red of the redox part and the ox, and it's combined to represent a redox reaction. But it's a little bit more specific than that. A redox reaction represents the process that happens when electrons are transferred between reactants. In this case, one substance is oxidized or loses an electron, and another substance, which is reduced, gains an electron. Now, the substance that's oxidized and loses an electron is known as the reducing agent, even though it is oxidized. The substance that is reduced and gains an electron is known as the oxidizing agent. So one facilitates the process of another. Now, it's important that as we proceed forward talking about oxidation and reduction reactions, that we become familiar with this idea of oxidation numbers. We'll get into that briefly after we discuss the idea of reduction versus oxidation. Now, oxidation numbers in an oxidation reduction reaction change during the reaction itself. And so we'll be paying close attention to those changes, but first we need to make sure that we understand our oxidation numbers. Now, from a basic premise, to understand our redox reaction, it features both an oxidation process and a reduction process. And it's important to understand what reduction and what oxidation looks like. The popular reference, Leo goes Ger, is employed when using oxidation reduction and identifying the process of what happens in this process. So this means that for losing electrons, when that process occurs, you have oxidation. When you have gaining of electrons, this alludes to the process of reduction. Now, let's look at an example. Here we have zinc reacted with copper sulfate, and they are broken down to an ionic equation that represents the transfer of these electrons. In this process, zinc loses 2 electrons. Therefore, because it loses 2 electrons, it is oxidized. Zinc also serves as the reducing agent. Now, copper gains 2 electrons. Copper is going to be reduced. It also is going to serve as the oxidizing agent. Now, in this reaction represented here, you notice an interaction between the copper and the zinc where there represents an exchange of these 2 electrons on a subatomic level. Notice the evidence of a reaction by the color change of the metal strip. Now, to label oxidation and reduction, we have to go through a series of rules for assigning oxidation numbers. First, elements that are left uncombined have an oxidation number of 0. This includes diatomic covalent compounds or exception compounds where they're covalently bond, such as oxygen or perhaps even ozone, O3. Aluminum, nitrogen, helium, zinc, all of these are notable examples in which when they're not bonded with anyone, they represent an oxidation number of 0. Now, the oxidation number must sum to the overall charge of the species. This means that if you have a polyatomic ion, the oxidation number should be that of the overall charge of the polyatomic ion. This also means that for a compound that is bonded together, the oxidation number of the entire compound should equal 0. So essentially recapping, this means that the oxidation number of the entire compound of sulfate is -2. And if we were solving for the oxidation number of S, we would use the rule that oxygen is usually -2 and conclude using math that our oxidation number of sulfur is +6. Now, these are an additional list of guidelines for assigning oxidation numbers. They include rules on fluorine, groups on 1A and 2A metal, hydrogen, oxygen, and group 7A. In the next slide, we have a list of the oxidation numbers found on many of the elements on the periodic table. Notice the arrangement of the oxidation numbers found in transition metals. This suggests that transition metals have a large capacity for displaying various oxidation numbers depending on what they are bound to. This also further suggests that some of the other notable ones can vary as well. And this gives you just a general idea of those oxidation numbers. Balancing redox reactions. So, the electrons, or in this case charge, must be balanced as well as the number and types of atoms. So, when we generally look at chemical reactions, we generally look at atoms and make sure that the balanced reaction is there to showcase the same number of atoms both on the reactant and product side. Well, when you balance redox reactions, there is a focus on making sure that the charge is balanced. So let's consider this net ionic reaction. In the following, we have a reaction between aluminum and nickel to yield aluminum nickel. Now, in this net ionic reaction, it's important to note that there is a characteristic charge of nickel and a characteristic charge of aluminum. these charges do not line up. It appears to be balanced as far as the number of type of atoms, but if you look closely, these charges are not the same, and so therefore consequently must be balanced accordingly. So let's revisit the reaction. We divide the reaction into two half reactions. First we have aluminum, which yields the following product. Next we have nickel, which forms the following product. Notice that you have 3 electrons transferred in aluminum and 2 electrons transferred in nickel. To get a common factor, you multiply each of the 2 electrons that are transferred to gain a common ground, and then apply those to the net half reaction. So in this case, 3 and 2 multiplied together yield 6. This means that if you multiply the 2 that are transferred here up here and the 3 that are transferred here, you can get a net balanced equation. You then want to cancel the electrons on both sides so that you end up with your original equation now featuring balanced charges. So here you have the balanced charge of plus 6 here, and you have a balanced charge of plus 6 here. Now, uniquely, they also feature the same number of atoms, both on the left and the right hand side. Disproportionation reactions. So, in this process, one element undergoes both oxidation and reduction. Consider, if you will, the reaction, or decomposition rather, of peroxide. This yields water and oxygen gas. What's interesting and unique about this reaction is that the oxygen that is featured undergoes both a process of reduction and a process of oxidation with respect to the original oxygen in the compound. In a displacement reaction, a common reaction that happens based on replacement of a metal, the active metal generally displaces a metal ion from a solution. In this case, magnesium displaces the copper metal and forms magnesium chloride, and this is copper solid. Now, the activity series of metals is most useful when predicting the outcome or unlikelihood of a reaction to occur. Looking at the following activity series, you can see how hydrogen is down here, and if you compare the previous, you have copper down here. And it's important to note that even though one may not need to memorize the activity series, there is a general trend that follows, and these values of reactivity or activity, it can be quantitated, and in many cases there's a chart provided when certain questions are asked about the activity series. Now, combustion reactions are generally high energy reactions that require some type of hydrocarbon starter fuel, and they yield a product of carbon dioxide and water. So consider the following reaction where you mix methane gas with oxygen, and this yields carbon dioxide and water. Now, concentrations of solutions. Now, the concentration is the amount of solute that is dissolved in a given amount of a solvent. The qualitative expressions of concentration are generally represented using molarity. Now, concentrated means that there's a higher ratio of solute with respect to solvent. A dilute substance suggests that there is a smaller ratio of solute to solvent. More specifically, as a method of comparison, one can both physically see the difference between a concentrated and a dilute sample. Here, represented in the 2 Erlenmeyer flasks, you see a concentrated solution, and as evidenced by its darker color, it is more concentrated than the latter product to the right. What is also noted is that per unit of volume, there can be found more solute particles in the solution than there are solid particles in the more dilute solution. So both from a physical and a chemical standpoint, one can see how there is a difference between a concentrated and a dilute solution. Concentrated features large amounts of solute present and generally has a darker color to correlate with that in some cases. And then dilute solutions are usually sparsely populated with the solute particles in the solution. Now, quantitative concentration term. As I mentioned, molarity represents the ratio of moles solute per liters of solution, and it is a widespread unit for concentration when you're dealing with chemistry. Now, molarity is equal to the moles of solute per liters of solution, and that is the equation before you. Now, the generic symbol that represents molarity can either be seen by a capital M, that's generally italicized, or by two brackets. Now, there are different forms of the molarity equation. Rewritten, it can be written as that. It can be written as that when solving for liters, or it can be written as that when solving for moles. Now, dilution is a little bit different. Now, the process of preparing a less concentrated solution from a more concentrated one is how you achieve dilution. Now, when you're comparing it, you compare the moles of solute before dilution and then the moles of solute after dilution. And this comparison can be used to obtain how dilution occurs. Now, the generic equation for dilution is as follows, where you're comparing that molarity and that liters of solution initially to the molarity and liters of solution following dilution, i.e. molarity concentrated, liters concentrated, molarity diluted, liters diluted. Solution stoichiometry. So, soluble ionic compounds dissociate completely in solution. And this is a known fact, as we've mentioned, both strong electrolytes and strong bases and strong acids tend to dissociate in solution. Now, if we use the mole ratios, we can calculate the concentration of all species found in a particular solution. This means that, for instance, sodium chloride dissociates into its respective starting ions of sodium and chloride. Sodium sulfide dissociates into 2 sodium ions and 1 sulfate ion. And there's a discernible difference there. Aluminum chloride is going to dissociate into aluminum plus 3 and 3 chloride ions. So we're going to use this to our advantage when we're calculating based on the species associated. In order to solve a question like this, where we're tasked with finding the concentration of all species in 0.25 molar solution of magnesium chloride, one must first write down the reaction to understand the 2 ions that are used. In this case, it forms magnesium 2 plus, and it forms 2 chloride ions. Given that the concentration of the total solution is 0.25 molar, one can conclude that the magnesium 2 plus has a 1-to-1 ratio, therefore its molar concentration is 0.25, whereas with the chloride, because it is a 1-to-2, it is a 0.5 molar concentration. Using the square bracket notation, we can express the molar concentration for all species in the following solutions. Barium 2 plus would be 0.42, whereas the hydroxide ion would be 0.84 because there are 2 respective constituent ions. In the case with the ammonium chloride, ammonium would be 1.2 molar because there's a 1-to-1 ratio, and then the chloride ion would be a 1.2 molar concentration because it's a 1-to-1 ratio. Aqueous reactions and chemical analysis. Alright, so there are types of quantitative analysis. They include gravimetric analysis, in which you look at a precipitation reaction, and then there's volumetric analysis. We are now going to take a look at the use of application of both processes. In the gravimetric analysis, you isolate the precipitate, and you can use the precipitation or precipitated substance or insoluble material, as we mentioned before, to determine what materials in concentrate with respect to concentration were involved in a reaction. Now, the typical steps involve requiring you to determine the mass of your unknown solid, dissolve unknown in water, combine with excess amount of known substance to form a precipitate. This excess drives the reaction to completion. Upon filtration, drying, and weighing of the precipitate, you can use that to extrapolate a value percentage and find the percentage of ion in an unknown solid. So let's look at an example. Here we have 0.25 grams sample of an ionic compound containing chloride ions, and an unknown metal is dissolved in water and treated with excess silver nitrate. If 1.725 grams of silver chloride precipitate forms, what is the percent by mass of chloride in the original sample? Steps to the solution. First, you're going to find the percentage of chloride in silver chloride. Next, you're going to multiply the percentage of chloride by the mass of the precipitate to obtain the chloride in the sample. Then you will divide the mass of chloride in sample by the total mass of sample and multiply 100 for a percent. To solve, we start first by finding the percentage of chloride. We take the molar mass of chloride and divide it by the molar mass of silver chloride to find its percent in silver chloride. We next apply this percentage to the silver chloride precipitate to determine the amount of chloride found in the sample. The percent chloride, therefore, in the unknown is calculated by taking the amount of chloride and dividing it by the 0.825 gram sample, and then we extract a value of 51.7% chloride. Now, for volumetric analysis, this is commonly accomplished using titration. Now, in this process, there's an addition of a solution that features a known concentration that is titrated into another solution of an unknown concentration. Standardization is the determination of the exact concentration of a solution. The equivalence point represents completion of a reaction when undergoing a titration. And the end point is where the titration is stopped. An indicator is usually used when titrating materials to show whether an equivalence point or an end point has been reached. These represent images of the apparatus that are used for titrations. It features a glass burette that has a knob nozzle that can be adjusted, and a Lemire flask that can be used for collection, and phenolphthalein indicator, which can be used to indicate evidence of equivalence point. Now, we are going to now calculate the molarity of 25 milliliters of a monoprotic acid if it took 45.5 milliliters of 0.25 molar potassium hydroxide to neutralize the acid. This mimics the instances where titration can occur. In this case, your known concentration is your potassium hydroxide that's being titrated against your monoprotic acid. The word monoprotic suggests that the acid features one ionizable hydrogen group. The reaction can be determined by first taking your moles of potassium hydroxide and multiplying that by your liters of solution, and then multiplying by the mole ratio, as it is a monoprotic acid, to get the moles of acid. Once you have obtained the moles of acid, you can then divide this by the liters of solution that were required to neutralize or reach the equivalence point in the titration. And once solved, you will achieve this molar concentration of 0.455 molar. So in summary, hopefully we have covered an extensive amount of information regarding electrolytes as they pertain to both strong and weak, as well as non-electrolytes. We've taken the time to discuss precipitation reactions and solubility rules that govern those precipitation reactions. We've also discussed molecular, ionic, and net ionic reactions. We've discussed acid-base neutralization reactions, redox reactions, or affectionately oxidation reduction reactions. And we've also taken the time to balance these reduction reactions using the half reaction method. We've talked about a few types of reaction, which consist of combination and other types of reactions. We've also discussed molarity. And finally, we've concluded with our discussion on solution stoichiometry as it relates to gravimetric analysis and volumetric analysis. That will complete our lesson today.